On. So welcome to my talk. So this is the Vulnerable Chemical Process Volume 2. So it is a continuity of my talk from the CCC. And interestingly enough, at CCC, I presented one of the possible attack scenarios, like the catalyst poisoning. And in my talk, my talk was about that hacking physical processes is not easy and also not trivial. And I'm really happy to say that that scenario did not really work out because it was too hard to implement. So we kind of switched to another attack scenarios, so which I will present today. So you've read my bio already. It's online, but so just in a nutshell, so I just finished doctoral research, still in the process of writing dissertation, and I just recently transitioned to the industry. And I know pretty much everything, or let's say a lot about traditional security, because I've been teaching almost all security subjects possible. But I still do prefer physics over web applications, so that's why I do cyber-physical security. And the most frequent questions which I get is just like, how did you learn all of that stuff? Like, is there any book? No, there is, until now, there is no a book. There is no even 2 or 3 books. Because so it's bits and pieces over many years, over multiple conferences and conversations, and maybe somebody has to write a book. And of course, learning by doing was the most effective, like always in hacking. So what is this talk about? The same, just because not everybody is really familiar with ICS and SCADA, just several words. So this is industrial control systems. This is what I'm talking about, which consists of basically of 2 parts of the IT system, which and the physical process itself, which is an application which needs to be protected. And so why the systems called cyber-physical systems is because you have the cyber layer and the physical layer. But since now the sensors become more smart and they become get the microcontroller embedded into them, so it's becoming a little bit difficult to understand where is the border between cyber and physical. Oops, okay. The sequence is not the same. Therefore, there is really the difference between embedded devices, when it's really you know where is the physics, where is the cyber, and cyber-physical system, where this border cannot be really clearly defined. So for this talk, if you don't know anything about cyber-physical security, for this talk you need to know what is control loop. So basically you have a physical process, you have sensors which measure the state of the physical process. So below you see the how that measurement would look like to the operator. You have a control system which consists of a lot of mathematical differential equations which compute their commands to the actuators, which adjust themselves. Basically, for example, the valve adjusts its position or the motor adjusts its speed. So in order to control the dynamic behavior of the process. So this is what you need to understand. And that slide's supposed to be before. So this is that analog sensor which you see on the photo. It's my own photo of the sensor which used still, for example, at our university. But now the sensors got this smartness, so this conversion from the analog to digital signal already happens in the sensor. The pre-processing of the data happens in the sensor. And in many cases, the sensors, which are called actually transmitters, that send data directly to the actuators without the PLC, without the controller. And they all now become IP-enabled, so you basically have Internet of Things right in your pipe. So this is the definition. So cyber-physical systems are IT systems embedded into application in the physical world. And in contrast to the traditional IT attackers, where they basically want to steal the information or credentials to perform further attack stages, the attack goal of the attacker in the SCADA systems is just to get the physical process perform certain actions or to bring it into certain state. basically, why do we need to worry? Is this because like this instrumentation really become smart? So this is like what a promise of the vendors, of the manufacturers. Expect instruments of the future to have multiple communication channel, each with one inbuilt security. Ha ha ha. Much like a present Ethernet switch. These channels will be managed with IP addressing and server technology, allowing the instrument to become a true data server. Do you really want to have the device inserted into your pipe carrying oil? I don't know. So this is why we need really to start studying how can we make processes inherently secure. And now we know that the attacker will be directly in our physical process. So we need to start securing the processes from the process point of view. So why do I study chemical plants? Like, somebody study cars, satellites, or airplanes. I study chemical plants. Well, they're very, very complex with extremely complex interdependencies and a wide variety of dynamic behaviors. They have a lot of disturbances. They have different modes of application. So it's extremely complex. And if you can hack this one, you can hack easier or physical processes. So typically, it is believed that, so here's your plan, go hack it. What will you start with? So typically, in the media, it's believed that there is some magic button attached directly to the internet, which you can press, and then you've done. So, but in reality, nobody still ever spoke how would exactly he execute that attack. And are there any other attack scenarios beyond like apocalypses? So basically, what can you do? So by now, we still even don't know what can we actually do to the process. So I classify possible like attack outcomes into three groups. First is the equipment damage. So basically, this is where you want to damage or destruct equipment or infrastructure, for example, a pipe. So the second group of attacks is damaging the production. For example, to spoil the product or to make production more expensive. That would make the final product, for example, more expensive and with that less competitive. So that would these two types of attacks. So for example, this is the comparative prices for a paracetamol. So the purity of the paracetamol. So if the attacker will manage to to mess up with the purity of your paracetamol, your losses are tremendous. So both two groups of these attacks will never make the front pages because companies typically do not disclose them and keep them secret. If you really would like to cause some publicity, then you would go for the third group of attacks. It's compliance violations. The most damaging attack would be attack on the occupational and environmental safety, which may result in the lethal accidents and serious environmental damage. A little bit less dramatic attack would be like pollution, for example, soil or water contamination. And that said, for example, in that case, from the business perspective, the plant may operate completely, optimally. But it will be non-compliant due to exceeding some concentration of the heavy metals in their emissions. That would cost a company lots of money in penalties and a very bad publicity. In certain cases, such plants can be shut down. And also the contractual agreements also can be very painful. So if the company will not deliver a product, they pay huge penalties. So, and the topic of this talk is how could we make production more expensive? So basically, how can we make a plant less profitable? So attack scenario is persistent economic damage. Persistent means that we want to avoid detection, and in cyber-physical world, it means that you have to avoid attribution of the event to to the cyber, like you want to avoid attribution to a cyber event and make them thinking that it's something like of natural causes. So they will keep hunting in the plant and will not be able to eradicate your attack. So for whom could be, this scenario could be interesting is, for example, for a manufacturer who would like to kick out its competitor out of the business and win new market shares, or for example, as a strong argument in the extortion attack. So, okay, so this is our attack goal. Let's start. So, in order to before you launch your malware, you have to test it. So, how do you test your malware on the chemical plants or any cyber-physical process? You need some test bed. So, of course, you can, for example, buy a plant, but it's expensive, and you have to deliver it. You need a lot of space. And secondly, if you, by chance, damaging, you need a new money to repair it. So the easiest way is to use realistic models like the simulated plants. So in my case, I use the realistic model of this vinyl acetate monomer plant. So this is very accurate model and has been used for 20 years by the process control and chemical engineers to develop their methodologies and strategies. So what is vinyl acetate? It's a building chemical for producing, which is later used for producing paints, adhesive solutions, plastic, and so on. It's producing tons amounts around the globe. One of them, it's really commodity chemical. So let's start. So I will now present you a complete attack from start to the end, and I'll show what it takes. And I will outline the challenges which is attacker is facing. So this is our goal. We need to put into our payload certain instructions to manipulate the process to achieve our goal. So typically, the attacker is not immediately gifted with a complete knowledge of the process or of the plan. So therefore, the attack typically goes through the certain stages, which is presented here, and I will go over all of them. But perfect knowledge is never achieved. Therefore, the attacker will need to go back to certain stages to repeat the same exercise, and sometimes to stay in this, repeat the same, let's say, stay on the same stage for some time. So we start with access. You need to get access to the plant. So this stage of the attack is the most familiar to any IT hacker. So you first have to get somewhere into the enterprise network, and the control and enterprise network are typically segregated with a firewall. So just use any ingress connection like patch management or database links or anything, and just get in. Of course, the closer you get to the process, there won't be traditional computers anymore, so you will probably have to invade field devices like sensors or so for example, Jason Larson, one of my main collaborators, he presented at Black Hat how to write rootkits for transmitters. So basically, this is a pressure transmitter. So basically, I will not stop at this stage because it is well known to everybody, but important to understand that this is the last stage where IT knowledge is useful to the attacker. After this stage, he has to start thinking as a process engineer. So in order to cause something to your, to achieve desired effects in the physical domain, you need to understand how your plant is working. So you need to discover it. So basically, you need to understand what and how the plant is producing. So even if you know that you are somewhere in the vinyl acetate plant, the exact physics and the chemistry is completely unique, and typically it is done and developed by third parties. So then you need to know how the plant is controlled, basically the position of the control valve, the tuning parameters, the control strategies applied, and control configuration. And also, last but not least, you need to know how the plant is built and wired together. So the first is a typical espionage. And what important to say is that process discovery is the most time-consuming among all the stages. And it's typically start like several months in advance. And all of those advanced persistent threats which we are now see online, which basically under the motto steal everything, this is exactly like to steal all of this information. Control is, in the control you also have to start doing reconnaissance, basically trying things and observing what is happening, but I'll talk about that later as well. So basically you need to find, for example, like kinetics of the reaction. As I mentioned, this is typically, you have, for this information, you have to go to some third parties. And for example, because the process operator, process owner, it's himself does not have this information. So in that case, the attacker will have even more advantage because he will have a more complete information. This is piping and instrumentation diagram. This is instrument list. And today morning, I was really lucky to find this treasure. So this was on the internet. So this is, you see, this is a screenshot of the asset management system. And you can see it is some pressure transmitter. You can see that it is, I don't know how well it's visible. So it's loop service. You see it is in the reactor unit. It is Yokogawa pressure transmitter. There is the exact model of it. We have process conditions, exactly all process conditions, what is the minimum and maximum, how it should be operated, and also the instrument range. So this is exactly what you need to figure out in this stage. This is my favorite joke, which I tell all the time, and people always amuse, that stripper is not an exotic dancer, it's a stripping column. So you really, really need to know and understand equipment. This is our, let's say, so we've got all of this knowledge. So now we know, okay, this is a model, this is a scheme of the plant. And we need to cause economic damage. Where do we start with? We can, of course, destroy the pipe which carries the final product. But that attack is, basically, it's too visible. It will be detected easily and fixed easily. So we will not be able to persist. The rest of the plant can be roughly divided into the reaction and refinement. Refinement, there is, like in the refinement section, for the attacker, there is a lot of opportunities to mess up. But also for the operators, there are a lot of opportunities to notice that something is happening and to fix. And also, at the end, you can still also send the non-refined product to recycle back and refine it again. In contrast, if we mess up with the reaction process in the reactor, we will basically make the refinement section redundant because we don't have the right product anyway, or we have too little product. So that sounds like a good attack scenario. We should probably concentrate on the reactor. But how do we exactly mess up with the reactor? For that, we need first to find out which controls are available to us in the reactor section. So this is the available controls. We located them, sounds good, but that's not all. Because if we look at the flows of the chemicals, we will notice that, for example, the acetic acid feed goes not only into the reactor section, but it also goes into the refinement section. It means if we will start manipulating something in the reactor section, we are running a danger to trigger alarms in the refinement section. So the attacker will have to monitor also the refinement section, which adds complexities. But this is exactly important to discover, because other than that, the attacker may trigger alarms unknowingly. And the attacker does not want to trigger alarms because he wants to go undetected. So understanding process typically operate on the so-called point abstraction. What it means, so everything what can be measured and everything which can be controlled, so basically sensors, actuators, are points. They are wired to some PLCs, to some controllers, and they have some code inside of the controller. So all of that has to be mapped by the attacker. This is one of the most and the hardest tasks for the attacker to achieve. For us, since we use a simulated plan, we have to locate required controllers and code within 6,000 of line of the C code of the process, which was not easy at all, I must say. So then the attacker has to, as I mentioned, the attacker has to reconstruct the control configuration. So this is like the violet, those dotted lines and circles, those are control loops. And why do we need to know them? Because you need to know like what to manipulate and where to observe the result of your manipulations. But that's only beginning, because obtaining controls, it does not mean being in control, because those controls might not be useful to the attack goal. And secondly, the attacker might not be able to obtain control. What exactly does it mean? I will explain, and with that we move to the control stage. So in control stage, we try to understand how the process dynamically reacts to the manipulations. So because once you hook up all these mechanical components together, they become related to each other not only by wires and controller code, but also by the physics of the process. So if you change some valve, everything around changes, and all of those effects propagates downstream and cause some effects somewhere in other parts of the plan. So all of those downstream effects has to be taken into account. So how much at this stage the attacker has to figure it out, how much the process can be changed before like triggering alarm, and like what the effects of those changes. Like there are a lot of parameters which influence those effects, and understanding each and single of them is essential for the attacker to understanding the response of the process to the manipulation. Because the attacker has to understand, is this effect, is it a result of my attack, or is this just a response of the physics of the process? Because without being differentiating these two, the attacker will not be able to understand how to design his attack. And one of the largest challenges, and really a headache for the attacker, is non-linearity of the process, of dynamic behavior of the process. What does it mean? So it means that the reaction or output is, of the process, or like say reaction of the process, is not proportional to the input, like for example to the control command. So it means, for example, if you heat a process from 130 degrees to 140 degrees, behavior of the process when it heated from 130 degrees to 140 degrees is completely different when it is further heated to 150 degrees. And typically, the behavior, physical behavior of any physical phenomena is known to us human only through the modeling, to the extent of the modeling. So we model those physical phenomena, and then we convert them into the control strategies, which we then load into the controller. So, for example, if the controller has, if the process has never been expected to be heated to 150 degrees, then the control algorithm has never been tested for its performance in this temperature range. And it means that most cases, controller will not be able to correctly control behavior of the process at some in the range which is outside of normal operating envelope. For example, in most cases, what happens, the process becomes unstable. Unstable process is not controllable process. So the attacker losing control of the process, so it means that he cannot construct his attack anymore. For example, in many cases, it's for example, if the attacker unskillfully manipulate the process, many control loops have so-called ringing. And the highest peak this is what will overshoot and probably will trigger alarms. So for us, it was really a large problem. So this is a badly tuned control loop, but most of the control loops are badly tuned. So we spent like a couple of weeks trying to overcome this challenge, so that eventually we could manipulate the process and achieve desired effects. So then we have to decide, so as an attacker, you have two options how you can, for the attacks. You can perform, for example, step attack, when you bring process to some stage and leave it there. Or you can perform like periodic attacks. When you launch an attack, then you let process to recover, then you launch attack again, and you let process to recover. Interestingly enough, that we figured out that periodic attacks are more effective for our goals than the step attacks. And then in those periodic attacks, we have two important parameters. It's magnitude of manipulation, so how much you can manipulate, deviate from the normal. And also, like, what is the recovery time? How much time the process needs to recover from this attack? And because the less time is needed, the more beneficial to attacker, because he can start launching a new attack immediately without, so he can launch it faster. So it means the economic damage will be larger and achieved faster. So these parameters will be important later for the attacker to evaluate like which control loops to use in the attack. So the outcome of this stage is the attacker has basically, like, after manipulated process for like couple of months, you get a mental process how the process behaves under attacks. But obviously, like, mental model is not sufficient. You need to kind of find the way to categorize, which we, for example, did in a table. So we found those control loops which can be reliably manipulated and really used during the attacks. So, for example, those and the other control loops probably would be discarded by the attacker. And also, we figured out the alarm propagation. Since, as I mentioned, we want to persist, so we don't want to trigger alarms. So we have to figure out, like, which control loops trigger alarms and what are the upper limits, like, of the manipulation. So now we know how we can control the process, and now we need to really start thinking how we damage it. So there could be several competing scenarios, and the attacker need to have a sort of metric or measure how to compare between attack scenarios. In general, there are two answers. There are or two, let's say, measures: technician and engineering. In technician, answer will tell us something will increase or decrease, and engineering answer will tell us by how much and how fast. So in the process engineering, everything what requires engineering answer is extremely hard because it is unique to the plant, unique to the operating model, mode, and so on. But technician doesn't give you the precise numbers. So, so the attacker, since the attacker wants to reduce the amount of vinyl acetate produced, he needs to find a way to measure the amount of vinyl acetate molecules in the reactor exit. So chemical concentrations are typically measured by the analyzers. And there are many analyzers installed in this plant, but none of them in the reactor exit. So the only because to quantify the amount of vinyl acetate produced, you need to know the flow and the concentration. And the only combination of those measurements is available to us at the decanter. But that measurements will be available to the attacker in 5 or 6 hours. So you perform an attack, and then in 6 hours you know how effective it was. So obviously it's not, it's ineffective. So we need to find a way to measure it somewhere in the reactor unit. So the only two measurements available to the attacker in the reactor units is temperature, exit flow temperature, and exit flow itself. And as you can see, unfortunately, this plant is not designed in attacker-friendly way. So actually, the exit flow temperature can be used as a technician answer. So the colder the exit flow, it means that less reaction is happening in the reactor, and it means that we produce less product. So this answer, this is a technician answer, and with observing the reactor exit temperature, the attacker may know that certain attack is effective or not, but he still cannot quantify how effective the attack. So we really need an engineering answer to be able to quantify something in dollars. And typically, so for example, if the measurements are directly not available, the attacker have to find a way to extract or find them. So for example, where can they be found? For example, in a testing plant. So each plant has a testing unit with a very accurate model of the process. And you can start looking there whether there is some intermediate measurements computed. Or you can look in the code, because in the controller code, they compute, there are a lot of intermediate measurements computed, which might be useful to the attacker. For example, we have to look into the controller codes, and that was really ugly differential equation, and it took us a lot of time to locate the right equation which we thought that we might be giving us concentrations. And we actually got the numbers which looked like this, and they did not tell us anything because they did not sum up to 1, they did not sum up to total flow, they look weird. So we thought that this is the right numbers, but we did not know what to do with them. Basically, 2 weeks of mathematical magic and 3 people, and eventually we were able to compute the concentration. And once we were really able to convert those numbers into the concentrations, we were able, which actually looks like this. We could then plot it. As you can see, it's really, this is now the engineering answer, and as you can see, it's really correlates with the technician answer. So, and eventually then we could quantify the product in dollars. So if you know, total product per day is $96,000 what they produce, and this is, for example, effect of one of the attacks, and you can see the product loss is 11,000. What I did not mention, in this particular scenario, we don't want to cause really dramatic financial damage, because if we cause it, then the operator will probably run to the government and tell I'm under attack, it's unnatural. So we wanted to do something what looks natural and what hurts, but not that much that they shut down the plant and start really investigating. So 11,000 is just like a border. It's already a little bit too much. We were targeting something like 8,000, 9,000 per day. So the outcome of the damage stage is that a portfolio of attacks, which can be, you can categorize them which damage potential they have. So, and then you just have this portfolio of attacks, and then you place them at the opportunity time. So as you see, there are some attacks which are less effective, economically effective, but they still can be useful in the cleanup phase. So what is cleanup phase about? So in the IT domain, the goal of the attack is to go undetected. And the cyber-physical or SCADA security is just simply not an option. If the attacker changes something in the physical world, that cannot be raised by simply raising the logs. So the operator will notice and people will start investigating. So the goal of this stage, and actually this stage goes in parallel to everything what we've been doing before, is to stage the attack in such a way that the investigators and the process operator will draw wrong conclusion, and they think it's something of natural cause and not a cyber event. Having operator in the control loop is actually what turns cyber-physical system into socio-technical system, because operators constantly monitor the process and can take over the controller to control the process. So in order to, let's say, to fool the operators, the attacker need to understand the specifics of his jobs and to find the vulnerabilities in his judgment, attention, and standard procedures he has to follow. And there are a lot of other humans involved in the plant operation. So the attacker wants to make the attack blaming on the operators and not on the cyber event. So since we are trying to stay under the radar, so we are not raising alarms, and we try to look natural, so the operator will probably not immediately notice that the process has drifted from the optimal economic performance. But once this decrease in the production will become persistent, they will start investigating. So for example, to look at this attack looking natural, the attacker, for example, has to time the attacks to specific human actions like recalibration, patch update, or maybe some shift of a particular employee or some weather events. Like each time when it rains, he plays an attack. Each time it rains, he plays an attack. So they will think that this is the cause of a rain and not of the cyber event. So for example, pick several ways how to increase temperature in the reactor, wait for the scheduled recalibration, play an attack, wait for the maintenance personnel to be screamed at, and wait for the calibration, play another attack, and so on. So this is, for example, result of 4 different attacks which cause deviation, like let's say deviation of the reactor temperature of 2 different, like of 4 different amplitudes. So just like play them in a different times. So eventually, when like they will think that they cannot fix the problem, they will probably start. The process operator will start doubting the reactor, and they will probably call a forensic team. There are specific people who can investigate, like there are chemical forensic people, and they will invite a professional team to investigate the performance of the reactor. And for the attacker, it is important to know which metrics forensics are using in order to understand, to analyze what is happening with the reactor. Because the attacker, again, wants them to draw wrong conclusions. So this is like typical metrics which forensics use in, like, what are those? Conversion rate and selectivity and so on. I will not explain what they exactly mean, but we also basically categorize also the attacks, so which cause, like, for example, only decrease in selectivity or in conversion rate. So congratulations, you just finished your first master class on cyber-physical hacking. So what are the conclusions? Why do we have to study all of this? Because the more we understand what it takes to execute such attacks, it gives us opportunity to make exploitation harder. So we need to understand what the attacker needs to do and how. So for example, as you can see, misbehaving control loops are actually beneficial to the defender because they make attacker life is much more difficult. If you know where the attacker has to go and which information to collect, you can wait for him there. Just monitor certain access rights and certain information must be obtained. Wait for the attacker there, or place the false information for the attacker as basically deception, apply deception techniques. And we can also start building more resilient processes. Of course, you know, like the new plants, the new processes, we can start building resilient by design, but there are also several things which can be done on the existing plants. For example, you can put additional manual valves which cannot be hacked. For example, you can decrease, so for example, fast valves are more beneficial to the attacker, so you can just retune them, make them a little bit more slower. I will not go into the details, but it's really effective. Yeah, or for example, faster control cycle is actually, again, for example, for the remote attacks, faster control cycle is disadvantages to the attacker. So all kinds of things. So that's all from my side. Thank you very much. And questions?
Thank you very much for your presentation. I have the following question. Which simulation packages can be used? Should I go to this GitHub page? Yes, we'll try to speak Russian. We have used 2 processes. This is a result of 2 years of our work, of many programmers and many sleepless nights. Vanilla Acetate plant simulation, but for this you also need MATLAB. But this is the best thing which you can do because MATLAB is available in many universities. It's free of charge for them because MATLAB it's open source SQL code which basically can be updated. But in order for you, so we have created simulative models for them where you can add new attack scenarios, and we have beautiful graphic user interface, and all these basic attacks have been implemented already in the graphics. Everything is beautiful, so we've done in such a way. So this is But tell me how the simulation is being done, the system of differential equations. Yes, the same thing as in normal controllers. Controllers have all these equations inbuilt in them, and it's done on a level of controller code. In other words, these models, I've been making a presentation. I was invited into MIST. It's a well-known standardization institute in America. They have used my models in their simulated testbed. They take data about process, physical sensors data, and they use them. Then they package them in databases. Then they send them by cable. So on a physical level, they use these particular models. But as I understand, this is for two chemical processes. Yes. Well, if you want to build models, it's very time-consuming. So most of universities or some companies, they build these proprietary models and they don't sell them. And even this simulational software, it's also, as a user, proprietary commercial. It costs excessive amounts of money and it's impossible to get it. It's not for daily people, but for you it's free of charge. Well, it's MATLAB, and yes, these two models, they are free of charge. Yes. Thank you.
Да.
Microphone, please. I don't hear the question. For the specific equipment, it's proprietary. Yes, this is the biggest difficulty of studying this particular topic, is that there is no available test beds. I understand. With equipment, you know about this equipment very closely. But I would like to specify several moments. You have specified, I didn't hear. What type of alarms you're speaking about? Safety, everything is when everything is being shut down, and operational is when you exceed. Not consequences it can lead to, but are these inbuilt engineering components or devices? Yes, when the plant is built and they start programming it. So it's programmable. Yes, it is programmable. So having good competences, you can go into the firmware and you can upgrade it to your level. That's how it is usually done. Alarms are suppressed. You can take a modern reactor, for example, and you can tell him that your pressure will be excessive with the excessive temperature and nothing will happen. Yes, yes. I understand this particular way of action, but your option is more elegant. Well, if it's an extortion attack, I have to keep under the radar as long as possible. It's not terroristic attack. Yeah, I don't want him to notice what really happens. So it's out of the competition wars. That's understandable. But another thing that I would like to specify about the discovery, at the moment when you say that, yes, you need to collect a lot of input data about how the process is happening. But truthfully speaking, out of my experience, very often in the area of IT infrastructure of every plant, everything that you've been described, yet this can be collected. And honestly speaking, this can be automated, and it's not so difficult. Yeah, it's not difficult to automate it. To collect this information, well, when I've started with SCADA security, Stuxnet wasn't available. In the internet, there was no information available at all. And every year, for example, even 1 year, there was no such amounts of information like right now. Right now, you can find anything. Yeah, we're trying. And unfortunately, what process operators don't understand, they really post all the screenshots, especially the fact is that the process is a constantly misbehave. So there's a lot of concentrations and a lot of companies who get a lot of money and debug it all the time. And for them, it's an advertising. So they constantly, if you will go to any consultant company, they will have 150 cases when they tell you in details how they've been debugging a certain control loop. And you will see everything with the pictures, with numbers, with screenshots, with principles. So for the attacker, you shouldn't do anything. You should go through the internet, you find anything. You just have to find yourself around in a place where you're going to do this attack. Okay. Thank you very much for your deep research. I have the following question. In many companies right now, in addition to control systems, they implement also improved APC, advanced control solution, APC, advanced plant solutions, so which are software means which allow them, which are over the system. They optimize the system, yes. So they develop special models, and the main idea is that the advanced control system undertakes, in the case of deviations, controllable values, it undertakes the control, and by influencing the executive mechanisms, it achieves some optimal values. So how they should behave in this case, if, for example, the attacker influences the controller, well, you can DDoS this thing on a switch. Well, in this case, this will become immediately obvious. The valid data. Unfortunately, I don't hear the question. It's not asked in the microphone. In the logs of SCADA, there is no big complexity here. When these systems are available, it makes it a little bit extra effort for the attacker. You also need to take care of this as well. Okay. And I have the following question about stand. In the beginning of your presentation, you shown us a big and in-depth model. So what do you think? Is it possible to somehow minimize this model? It's already minimized, because you cannot model the whole plant, but in order to do the informational audit, for the audit purposes, is it possible to somehow minimize this model and make it in order to do the informational audit? What do you mean for the informational audit? Well, if you have a task to do the information security audit in the company, right? Which model, according to your opinion, will represent in the best way to be able to say that informational audit is on a proper level? Well, in this case, this model is not so useful, because these models are used to study a lower level of attacks. But for the audit purposes and for the IT audit, it's not going to be useful. The only thing they can be useful in cases if during this audit you have discovered certain vulnerability, and you can say that yes, this vulnerability will lead to this effect. Then you can use models and you can demonstrate which effect it might lead to. For example, Alan Leverett has presented his vulnerabilities in switches, Ethernet switches, on CCCC. He will make a presentation on Black Hat and DevCon, and Friday I will make a presentation on Hack in the Box. I will show them what can be achieved with the help of these vulnerabilities. What is the danger in them? Because yes, there are switch vulnerabilities, but what specific dangers it can lead on a plant level, and it will demonstrate which attacks can be done and what's going to be their effect. So for this purpose, you can use those models. And where this presentation will be done? Hack in the Box, it's going to be next Friday. I don't know whether they will broadcast it, whether it's going to be online or not. I don't know, not yet. Where will this happen? In Amsterdam. In Amsterdam. Okay, thank you. So right now I'm jumping into the airplane, flying there. I don't hear the question, because it's not being asked in the microphone. Thank you. In this scenario, yes. For example, in my case, it did happen that not everything was modeled. For example, catalyzer, you can dilute the catalyzer, but it also something that happens in a reactor. Well, in refinement, there's other things which can be done in order to make lesser purity of the product, and because they divide those chemicals into components. But if the division didn't happen completely because there's a certain specification to the product, there should be no more than 3% of add-ins. If at the output they don't have it, they should collect it into the boxes. They should refeed it into the refinement and do the second refinement and pure it for the second time. But if they did it for the second time and they weren't able to do it for the second time, they will do it second, third, and fourth time. So it takes a lot of headaches for them. And perhaps they will have to stop production or will ask another plant to do the purification. Unfortunately, we have very tough schedule, so if people have questions, they can ask those questions outside of this room. Thank you.